All right, we've got a couple graphs here we want to evaluate. The first one is rate versus reactant concentration, which you can think of as rate versus, and then brackets A, the concentration of A. You see that A is the x-axis, rate in molarity per second is the y-axis. A couple things we want to notice about that, and we'll come back to it. We've got a different type of graph you'll see sometimes, which is reactant concentration versus time. So we've got concentration on the y-axis, time on the x-axis. So a little bit different graphs. So as concentration changes, what happens to the rate? Well, with a zero order reaction, we know that it's independent of the concentration. The rate is independent of the concentration. So the rate stays constant when concentration changes. That's why it is a flat line. A first order reaction is going to be directly proportional to the concentration of A. So it's got a slant, but it's a constant slope. It's a straight line. Then you see this blue one. That is the second order reaction. You may recognize that that is very similar to some graphs that you've seen of squared functions. That's because this is a positive number being squared as you go along, so it's curved. I'm not going to go into detail about that, but just be aware that if it's a curved line, it's not first order, it's not zero order, it's most likely going to be second order. But we'll talk more about that later. Now looking over at the other one, where we have the concentration on the y-axis and we have the time on the x-axis, the slope of the concentration of A versus time is the speed of the reaction. That's how quickly the reaction is happening. A zero order reaction has a constant rate. The speed is constant no matter what time. The slope stays constant with time, so the speed stays constant. That means it's the zeroth order reaction that does not depend on the concentration. Okay, that's it for the graphs. We'll come back and do some more of those in a later set of notes. Let's do some practice with an actual chemical reaction doing rate law. So I've got experiments 1, 2, 3, 4, and 5. I've got some concentration units that are a little bit different, but we can still use those. Okay. First, we want to determine the rate of consumption of NOCl in experiment 1. We want to determine the order of the reaction with respect to NOCl and justify our answer. Write the rate law of this reaction, determine the rate constant for the reaction, including the units, and calculate the rate in experiment 5. Let's first do part A. Determine the rate of consumption of NOCl in experiment 1. Now, when we're consuming something, we're going to use a negative number. It's the consumption. Okay? If we're producing it, we'll use a positive number. And I notice the coefficient of 2. So that means that I'm going to consume this twice as quickly as the overall reaction takes place. So if I know the initial rate for experiment 1, I just need to multiply that by -2 in order to get the rate of the consumption of NOCl. Note that we use the negative sign for reactants because they're being consumed. So I get -2 times 5.98 times 10 to the 4th molecules per centimeter cubed times second. You get -1.20 times 10 to the 5th molecules per centimeter cubed second. Second, we want to determine the order of the reaction with respect to NOCl and justify our answer. So if we compare experiments 1 and 2, and we use our rate law expression, rate equals K times the concentration of NOCl to some power n, and I know that that's my rate law because I only have one reactant. I just need to determine the order of the reaction. So as I went from 3.0 times 10 to the 16th to 2.0 times 10 to the 16th, how did that affect the initial rate going from 5.98 times 10 to the 4th to 2.66 times 10 to the 4th? Let's set up a proportion. So my rate, 5.9 times 10 to the 4th over 2.66 times 10 to the 4th equals K times, and then we've got the concentration 3.0 times 10 to the 16th over 2.0 times 10 to the 16th, and we've got that, of course, multiplied by K and raised to the n power. We can't cancel out that exponent, by the way, but we can cancel out the K's. When I divide this out, 3 over 2 is 1.5. 10 to the 16th cancels out. K cancels out. The 10 to the 4th cancels out. And this is essentially 6. Anyways, you can divide it out to get a more exact answer. You get 2.25 equals 1.5 to the n. Well, what could I raise 1.5 to? What power could I raise 1.5 to get 2.25? Hopefully you can recognize that if I squared it, if I raised it to the second power, I would get 2.25. So this is second order for NOCl. Should have written NOCl right there. Part C asks to write the rate law of the reaction. So the rate law would be rate equals K times the concentration of NOCl squared, because we just found its second order. Determine the rate constant for the reaction including the units. So we're going to plug in numbers from one of our trials. I chose experiment 1. And K equals rate over concentration of NOCl squared. I just rearranged this equation to solve for K. I divided by NOCl squared. So I have my rate from trial 1, and I included the units, molecules per centimeter cubed second. And then I put 3.0 times 10 to the 16th, that's our concentration of NOCl, molecules per centimeter cubed, and I've got to square that. When you square something that has a power, you're actually going to multiply your power by 2. So when I divide this out, I'm going to just work with the units first. We have 3.0 times 10 to the 16th squared. I've got 5.9 times 10 to the 4th molecules per centimeter cubed per second. And then down here I've got molecules squared, centimeters to the 6th power. When I do the math, I end up with 6.6 times 10 to the negative 29th. And now let's look at our units. Molecules up here, that's to the first power, minus the second power. Centimeters to the negative 3rd, minus negative 6, which is just plus 6. And then I have inverse seconds. So now we just are going to do the little bit of arithmetic to find out what the units are going to be. We end up with 6.6 times 10 to the negative 29th molecules to the negative 1, centimeters cubed, seconds to the negative 1. You may come across a question where you have to come up with some unusual units like that, so you want to be familiar with this process. Okay, part E, calculate the rate in experiment 5. So we've got experiment 5 here, we just need to plug it into our equation. Rate is K times NOCl squared, and we figured out what K was, 6.6 times 10 to the negative 29th inverse molecules times centimeters cubed times inverse seconds. We'll plug that in and multiply by the concentration, 2.5 times 10 to the 16th molecules per centimeter cubed. And we've got to square that. When you do the math, you find that your units are molecules squared, centimeters to the -6th for this component, and we get 6.25 times 10 to the 32nd power here. Now we need to multiply those numbers, and we also need to multiply our units. So we end up with 4.1 times 10 to the 4th molecules to the -1 plus 2. That's going to be just molecules. Centimeters to the 3 minus 6, which is -3. And then seconds to the -1. And there are our units.